behavior is what it sounds like. It's what is happening at the ends of the graph as we go to positive infinity and negative infinity. So the end behavior of a function describes how the function behaves. Behaves. I can spell. Okay. Is it moves infinitely to the right or to the left. So in other words, the end behavior describes what happens to the value as y as x increases or decreases without bound. And what we're going to be using for this is limit notation. Okay. So left end behavior is going to be what's happening at negative infinity. Right end behavior is going to be what's happening at positive infinity. So the notation for limits, and limits just show us where the graph is approaching. The limit as we go to the negative side is going to be the limit as x goes to negative infinity of our function, otherwise known as the x values decrease without bound, the y values such and such. On the right end, we're going to x goes to positive infinity. So as the x values increase without bound, what's happening to the y values? So we're going to look at some graphs and we're going to describe what's happening at the left side and the right side. We're going to do this verbally and with that limit statement. So the left behavior verbally as we're going this way. So as x decreases without bound, f of x, or the y values, well, as we're going to negative infinity, the y values are going to keep getting bigger and bigger and bigger. So the way we'll describe that is f of x increases without bound.
You have to put f of x if you put y.
Okay, the way we're going to say that same thing with limit, so we do lim. Underneath that, we say x goes to negative infinity of f of x, and it's going to positive infinity. So as my x values are going to infinity, f of x, or negative infinity, f of x is going to positive infinity. The right-hand behavior, we're going this direction now. So as x increases without bound, my y values, or f of x, on this graph, the y values are going to negative infinity. So we'll say f of x decreases without bound. Okay, and then how we'll say that with a limit statement is the limit as x goes to positive infinity of f of x. Since these are decreasing without bound, they are headed towards negative infinity. So let's look at this other graph. As x decreases without bound, f of x, or our y values, so as we're going to negative infinity in the x direction, in the y direction, those values are also increasing. So f of x increases without bound. For the limit statement, it's always the limit as x goes to negative infinity, and I'm going to say f of x. Since they're going up, we're going to positive infinity. Okay, so for the right side, as our x increases without bound, on that graph, f of x is going up to positive infinity. So f of x increases without bound on that direction as well. Okay, and then our limit statement is going to be the limit as x goes to infinity of f of x for this particular graph goes to infinity. In this next example, we're going to sketch a graph with the following end behaviors. So this one, as x goes to negative infinity, f of x is going to negative infinity. As x goes to positive infinity, my function values are going to negative infinity. So there's lots of different ways you can draw this graph, but what we're worried about is as our x increases, the function is facing down, because in both directions it's going to negative infinity. Okay, what happens here can look like whatever you want it to, but at the ends it needs to be going to negative infinity. Here, as x goes to negative infinity, my graph is going to negative infinity. As I go to positive infinity, my graph is going to positive infinity. So I'm just going to do something like that. Okay, you can really draw it however you want, as long as these ones are increasing and these ones are decreasing. Okay. So yeah, for polynomial functions, the degree in the leading coefficient is going to determine what happens as we go to positive and negative infinity. So we're going to first look at if I have an even degree polynomial, so 2, 4, 6, 8, and the leading coefficient is positive. My graph is always going to look something like that. It might be just a parabola, it might have lots of little wiggles in there, but at the ends it's going to behave the same. So we're going to fill in our limit values. So the limit statement is always, the limit as x goes to negative infinity equals, and the limit as x goes to positive infinity. Okay, the thing that will change is what we're putting after those equal signs. Okay, in this case, as I'm going to both positive and negative infinity, our function is going to positive infinity. So if we have an even negative, our graph is going to look more like this. So this does have a global maximum. My limit statement. Okay, and I'll just write these out just to emphasize the fact that this is always the same for the limit notation for end behavior. What we fill in the blanks with will depend. So on this graph, where are each of our y values going? Okay, so they're going down. Okay, so even degree polynomials, both ends are going to go to the same. Either they're going to go to positive infinity if it's positive, if the leading coefficient is positive, or they're both going to go to negative infinity. Okay, an odd positive is going to look something like that. Okay, again, here you might have lots of bumps, you might not have any bumps, but at the ends, if we have an odd degree and a positive leading coefficient, okay, as we go to negative infinity, my graph is going to negative infinity. As we go to positive infinity, we're going to positive infinity. The odd negative, we'll flip it over. Okay, and then the end behaviors are going to switch. As we go to negative, now we're going to positive infinity. As x goes to positive infinity, our function is going to go to negative. So this chart is something that you'll need to know, but if you can picture the graphs and understand how even degree polynomials behave, how odd degree polynomials behave, then you're in business. With that chart that you're going to memorize, now we just have to identify, I don't need the graph in front of me to be able to determine the end behavior. I just need to identify the degree is even or odd, and if the leading coefficient is positive or negative. So this one here is an even degree polynomial with a negative leading coefficient. So when you're asked to explain, that's what you're going to say. Okay. In my head, I always just kind of jot myself a little graph just to kind of, okay, it's an even negative. That means they're going the same, but they're going down. And then I'm going to fill in the limits. So always the limit as x goes to negative infinity, and the limit as x goes to positive infinity. Okay, so we're decreasing without bound for both of those. Letter B is an odd degree with a positive leading coefficient. Okay, so it's going to behave something like that. Okay, now this one, we got to be careful. The name of this guy is different. This one is g of x, so what we put here needs to be g of x. Okay. This one, as we go to negative infinity, we'll go to negative infinity. And as we go to positive infinity, we're going to go to positive infinity. So we're going to use a graphing calculator. This one we don't need a calculator. That one is one you will be expected to know how to do without a calculator. These ones, however, for right now, we are going to use the calculator for the end behavior. In our next unit, you will be able to do those without a calculator. Okay, so let's first look at g of x. Did it in my last class? Okay, so I'm going to go ahead and use, you can either use the fraction or just use parentheses. 3 and x plus 1. Okay. I'm going to start by graphing this on just a standard window. So if you do zoom standard, that'll reset your window to negative 10 to 10 and negative 10 to 10. So what should kind of become apparent, and I'm actually going to zoom out, is the graph isn't just increasing or decreasing without bound. It's actually approaching a single value. If I change my window, I'm going to go from like negative 20 to 20. And we're going to see this graph has what we call a horizontal asymptote. This side of the graph is approaching it from the top side. This side is approaching it from the negative side. So if we trace, let's first look at negative infinity. Okay, if we look at those values, or look at kind of the graph, what does it appear those values are approaching as we keep going negative? Okay, so as we're looking at this, and you could keep tracing out if you weren't confident on that value, but what's going to happen here is these values are going to get really, really close to 2. So our limit as x goes to negative infinity of g of x is going to be 2. And as we go to positive infinity on this graph is 2. Okay, again, because there's a horizontal asymptote there. Okay, and it's just going to keep approaching it. That's the advantage of a limit, because a limit is really what are we approaching. We're never going to get a value of 2 out of this equation, but we're going to get really, really, really close. Okay, let's try the next one. Okay. So we graphed this last one. Okay, and I think this one's a little bit clearer because we actually have a physical line that we're approaching. As we go to negative infinity, what are those values approaching? And they're not going to cross 0. And same for positive infinity, okay? It's not going to keep going up or down like we saw in some of the other ones. This has a limit, a left limit. And we have h of x this time is going to be 0. And my limit as x goes to positive infinity on this one is 0. Okay. Again, we get to do this by hand in our next unit. But for this one, we get to use the calculator. So that is polynomials and end behavior.